Okay, welcome to our discussion of how a milking machine works. So, what are the parts and what is the theory on kind of a generic milking operation? So, start of class, getting things started here. Labs are going to be postponed in the short run. We talked about making a plan, evaluating a farm. I don't know if they're going to bring us back to campus or not. If they do, we'll do that farm evaluation here, or I'll have to come up with something alternative. I'm moving in that direction. I assume we're not coming back to campus. Milking theory. How does milking work? Um, Basically, it's about milk flowing from areas of high pressure to lower pressure. If we look at hand milking, we're looking at something that is a positive pressure system. We're increasing the pressure in the udder and therefore forcing the milk out. Our milking machines are more of a negative pressure system where we maintain the normal pressure in the udder or the teat, and the outside is a vacuum, and then again, the milk flows from a high to a. See if I can get my uh, laser pointer going here. So with positive pressure, we pinch off the top, we squeeze or pull down on that teat. We increase the pressure on the inside of that teat cistern. That forces the milk out into the lower pressure outside. This is atmospheric out and around, but inside that teat, with our milking machine, we're creating a negative pressure. We have the teat here, the teat cistern in, the milk is at a normal pressure. But during a milking phase, we have a vacuum out here, a negative pressure. The milk flows from a higher pressure to a lower pressure, and the milk during the milking phase of the milking machine just runs out of the teat end. And we'll show you in a separate video how that works. If you've been on campus, you could have seen it firsthand, but I did a short video that we'll post, and you can take a look at that. So if we look at milking machines, they're pretty much the same method, same principles since the 1800s. So over a century, they've been the same way. So we have two phases on each teat. We have a milking phase and the rest are massage phase. And the teat cups that go over the teat alternate between these two phases to keep the teat end healthy and to draw out, excuse me, the milk during the milking phase. So here we have the teat cup, the rigid lining. We have the liner, the black here. And we have these disturbingly blue teats, but I guess that's a function of the publication. They only had those three colors, and that's what they had to work with. So we have the milking phase and the resting phase or the massage phase. So during the milking phase, the liner is open, it's not collapsed. And in order to do that, we have vacuum on the outside of that liner in the shell, and then we have vacuum at the teat end. So with our teat cup, what alternates is the air pressure in the outside of the tube. Inside the liner, the milking is a constant vacuum. What we have is an alternation between vacuum during the milking phase and then regular atmospheric pressure during the rest phase. So we have a negative pressure and then a zero pressure. So this is higher than what's on the inside. That's going to collapse the liner down to remove our rest or massage phase. So milking, the pressure is the same on both sides. The liner is open. The higher pressure here, lower pressure there. The milk runs out into the tube, the short milk tube, to the claw, and on to the um, collection system. During the rest phase, we have atmospheric air entering this liner that becomes a greater pressure than what's on the inside. That collapses the liner, pushes it in. That's going to pinch or squeeze the end of the teat, and it's going to push the blood and the fluids back up into the udders. So we get regular blood flow during milking. We don't have blood and lymph, uh, bodily fluids congesting down at the end of the teat end. So these are the two phases. We alternate between those with the use of a pulsator. I'll demonstrate in a little bit what a pulsator does or how a pulsator works. I have one I can take apart. I'll film myself doing that and we'll show you how things work that way. So getting back to that, we have the 4 teat cups. They're dual chambered, so we can have that alternation between the milking phase and the massage phase. They all have a rigid outer liner, a flexible inner liner. Over the years, the materials these things have been made of have changed and evolved, and they've tried different things, but the principles are the same. Rigid outer shell, flexible liner that can open and collapse as it needs to. Those 4 chambered teat cups are going to drain into a common claw, and we have milk lines and vacuum lines that provide the necessary um, supplies, milk to get to the collection area, vacuum to get to the teat cup as it's needed. So we're looking at those parts. We have the 4 teat cups. Some lines are missing here. You're going to have usually a design when these are flopped over. You're holding your hand underneath here, lifting that up so the air is cut off so you're not sucking stuff in through the teacup when they're flopped over. That's going to help preserve the vacuum in the system and allow the other machines in the system to stay on. So we usually lift those up, we pinch those off, bring those up, put those on a teat. So we've got the short milk tube here that goes from the teat cup to the claw. Sometimes they're all one piece. On a farm, I used to change the liners for my dad. They were 2-piece. We had one that went in here, and then there was a plastic piece, and then there was another piece there. So short milk tube separate from the liner on the inside. And then the long milk tube leaves the claw and goes to the central milk collector. We have the, what are they calling these? So the short pulse line here from our central distribution system, vacuum coming in from the pulsator, and then that air coming in and out is distributed up in those lines moving through. So mouthpiece at the top, we'll use that line, the liner in the barrel, the outer hard shell, the pulsation chamber around that liner, your cutoff there, and then you have some sort of valve that you can start and stop milking, and you're doing that manually. We have lines that will pinch off automatically with automatic takeoffs, like you'll see at the dairy. A clamp comes down and removes the vacuum from the machine, and then the claw is retracted. So the teat goes into the teat cut, the rubber liner, silicone liner, whatever it may be, is pulsated. The outer and inner chambers, when they're both under vacuum, that is when the milk flows. So the milk is not squeezed out by the collapsing liner. It is drawn out by the vacuum when the chamber is open, not the other way around. That's a common misconception. When the outer side is atmospheric, that's when the pulsator lets in atmospheric air that goes to those outer liner there. The liner collapses because the greater pressure on the outside than the vacuum on the inside. That collapses and massages the teat end. It doesn't squeeze out the milk, it massages the teat. We want that teat to go down to a wedge, and you'll see that in the video I'll be posting for that. Milk flows to the claw. There's usually some sort of inlet somewhere along the way that pushes that milk along the line to a central collection area. So you're going to lose some vacuum. We talk about vacuum level in the system. If you're out at the dairy, we have it up at the front end of the parlor. If you look up, there's a vacuum designation, says how much vacuum is in the lines at any one time. Milking rate is very much influenced by the vacuum level. The greater the vacuum difference, the greater the milking rate. So we're drawing milk across a high to a low. The greater the difference between that high to low, the faster the milk is going to move out. So our operating vacuum is usually a compromise between an acceptable milking rate and minimal teat end damage. The greater the vacuum on the end, the more likely we'll have teat end damage because of the pressure differential therein. The lower the vacuum, the slower the milking rate. So we usually try for a goal in most milking systems of 12 inches of mercury is the measurement we're using or the units we're using at the teat end. So our operating vacuum is usually around 15 inches of mercury. So in the main line, in the main vacuum lines, we've got 15. As that vacuum works its way down to the end of the milking machine, the teat cups, it usually falls a few inches, and we're usually around 12 for our teat end vacuum. Pulsation. When we're doing our pulsation, the liner opens and closes. We usually do that about 55 to 65 times a minute. We want to have adequate time for the liner to completely collapse. If we did a too high a rate, the liner would never fully collapse. If we increase the rate, one of my professors talked to me about um, increasing the rate so him and his brother could get done milking faster. Will that increasing the rate of cycles increase the milk out? The answer is no, because you're going to spend a certain amount of time in each cycle in the milking phase and a certain amount of time in the rest or massage phase. Doesn't matter how many cycles you're going to go through, you're going to have the same amount of time. And at some point, you may increase it to the rate where you're just never collapsing. So if things are not working the way they should, it's going to cause more problems. So we've evolved to that 55 to 65 cycles per minute. The pulsation ratio, the ratio of milk to rest and massage is somewhere between 50-50 and 70-30. So 50% of the time in the milking phase or 70% of the time in the milking phase. The rest is massage phase. I think we're 60-40 up at the dairy. So the longer ratio, the more time you spend in the milking phase, the more the milk will be drawn out. If the milk phase is too long relative to the massage phase, you're going to get more congestion in that teat end and more potential for teat end damage. If the milking phase is too short, you're going to really slow down the milk out. So trial and error over the last 100 years has brought us to those ratios. When we're thinking about pulsation, we can have all four pulsate teacups pulse at the same time. That is a more antiquated system. Now, more often than not, we'll have two teacups alternate with two other teacups. So you'll have a dual chamber pulsator, which one controls two teacups, the other controls the other two. The advantage of that, and the reason we've gone to that, is it tends to even out the milking flow. Instead of all four teats removing milk and then they all stop, all start, all stop. We've got start, start, start. So they're all flowing and you get a more even flow. You don't get the pressure drops the vacuum drops at the end of the teat end, things tend to be more even and you get a better milk out and better teat end health. So most systems now have that alternating. Some do diagonal, some do front back, some do left right. I think the ones at the dairy do front back. Um, I don't. It may be more beneficial to go left right, um, just to even out the flow. Um, you got more milk in the rear than the forudder, so it might even out better if you did left and right. But the one we have at the dairy, as you'll see, is kind of front back.